Exercise 21 corresponds to 8.1.3. So we show that the category of finite-abelian groups is denoted by abelian groups and F isomorphic to its opposite category, which means category equivalence to its opposite category, finite-abelian groups up. Okay, so notice that for finite-abelian groups, this is just a finite sum of the form z quotient by some integer mi. Let's say finitely many, such that m1 divides m2 divides mr. And if we require this division relation, there is this unique series m1, m2, mr. Okay, and we're going to construct this functor. What we do is, let's just define it on z quotient by some integer, and then it's just for direct sum, finite and direct sum. Let's just extend by commutativity with this direct sum. Okay. And it suffices to just check this. For example, suppose we could prove so the essential research activity is obvious. Suppose we have constructed this functor, okay, and then we could prove it's fully faithful, which means F then does it imply for the experiment we still have the bijection by our definition of F? This F is just F of the experiment of F. Okay, this is still okay. It's because this is finite direct sum, and so this is the same as product, the same as coproduct, because this is in the category of same modules. Here we don't know, it's R, right? So S. And so you could move this outside. Basically, we could move the product in the second position outside and move the coproduct in the first position outside, and so both those could be moved outside. Similarly for here, and so finally it will reduces to let's check isomorphism here. So let's construct this functor in the level of object I already defined, which is this. And so in the level of morphism is just for any map from Z to Zn. This is map to morphism. So opposite category. You could write this if you want. Yeah, it's just this, which means the same thing. Which means the morphism identifies under the bijection home set between the category as its opposite. Sorry, conversely, B2A. If you want, add up here. Okay, this is morphism. So let's check. So the important thing is to check it's faithfully. That's what you have to check, which requires computation. So let's compute precisely what is this home set, the finite-abelian-Groups from quotient f to the quotient n. Take arbitrary map here. So it's uniquely determined by the image of the multiplicative identity 1. Suppose this is mapped to alpha bar. And so f is uniquely determined by this alpha bar, but this is not arbitrary alpha. It must satisfy 0 map to 0. 0 is m bar, so also equals m times 1 bar. And so f0 equals 0 would imply that mf1 bar equals 0. Imply that m times alpha bar equals 0 bar, which implies that m alpha fall into n, so it should n divides. So if we take the greatest common divisor, divide by greatest common divisor, of n and m, it's denoted by t, and this is just m prime t alpha, I mean n prime and m prime coprime. And so this implies m prime divides m prime alpha, prime divides alpha. Basically, this is saying that for alpha, actually this is only restriction. Okay, this is only restriction. Basically, this is telling that your alpha have to satisfy that it is divisible by n divided by t. And this is telling that this home set actually is bijective with just choosing alpha, make sure that the alpha is a multiple of n. Actually, it's determined by alpha bar, right? So what is choice of your alpha? It must be divisible by n bar, n prime, sorry. And Tn prime is already n. So basically, sum of this equation by T. And the map is your f is determined by your f1, but your f1 is alpha bar, which is divisible by n prime. If you divide it by n prime, it will be one bar, 2 bar until T bar equals 0. So let me be more precise. There is a map by mod T because T divides n, so this makes sense. Okay. This is how you map your f1 to. Let me write this to make it more reasonable. But notice that this is telling you at the same time we want to prove the free faithful. What is the op? Let's just do the computation. So change the position of x and y. You have to show the homomorphism from Zn to Zm is isomorphic to the homomorphism from Zm to Zm. This is the case here because this is again isomorphic to the equation by T for the same reason. And basically this finish the proof, and of course you could also check that f is indeed a functor. For example, you could also check if identity is identity and f maps composition to composition f. Just check it. Basically that's the main part of the proof.